All right, so our issue was the square term has this 2 in front of it. And that's what makes things a little trickier in terms of how we handle this. So we talked about 2 different ways we can look at this. One way is, and I think people really understand this pretty well, it's just over the long haul, not the most efficient way, but it's a nice visual. It's a nice way to kind of organize information. That is with our little area model. So when we do these with this x squared here, we know that this would be x and x. The difference now is when we put a 2 in front of this, what that now means is we have 2x squareds. So one way we can kind of model that now is with 2 perfect squares, where we also have an x squared right there. Then whenever we did these and there was just a 1 in front of it, this number right here, we always got from these 2 boxes. But now that we actually know we have 2 different squares, those 20x's have to be divvied up between these 4 boxes. All right. So if we have 20x's total, how many go in each of those 2 boxes? See him? Good. So each one of those has to be a 5x. So we put some 5x's in there. That then means across the top of these, we have to have 5s. All right. That way we get the 5x's in each of those 2 corners. So what I am about to create, so when I now write this as y equals, and then what we now have, notice how we have an x plus a 5 up here. We have an x plus a 5 right there. So we have x plus 5 squared. That's one of them. That's what we spent a couple of days doing. But now notice we have 2 of them. So if I just slot a 2 in front of this, that accounts for both of these area models that we have set up. When we set these up, the 5 and the 5 now, the last part of this means we have 25 constants in this square. We have 25 constants in this square. So one way we can approach it is, again, this whole little thing with the area, knowing that when I write this right here, so when I write this, I have 50 constants accumulated in this model right here because I have these 2 squares. Well, if I have 50 total, is 50 how many we had in the original problem? No, we have a negative 10. So one way we could do it is what we have been doing. If I need to go from 50 down to a negative 10, wouldn't we for sure have to subtract? We need to decrease 50 by quite a bit. And I would need to decrease 50 by how many to get down to a negative 10? All right, Maddie? 60. Good. So that is one route we can take. All right, we are all the way down to the negative 60. So we then know that this is our vertex form. If I now ask us to graph this or find the vertex, we now know the vertex, once we have it in that form, is a negative 5, negative 60. All right. Now, the other route, so again, it's sort of up to you. The route I'm going to do right now is a little more efficient. It's not a great visual, but now that we have the visual, as we do this one, we'll be able to reference these guys. So what we were showing you yesterday is when we now do this problem, what we've been doing pretty much in all of these, we ignore the 10 until the very end. We just did it here. We kind of ignored that 10. We adjusted at the end. And what we really just work with are these first 2 terms. Well, if we know down here that we ultimately want the number in front of this x right here to be a 1, then the way we're going to create that is by whatever number's in front, we just want to divide that by that number, and then we do the same thing to this second number. Then that 2 is basically now out in front, and what we would have is an x squared plus a 5x. Wait, sorry, stop. That's a 20, sorry, right, 20. I started to think ahead of it, I was like, that's not going to give us the same thing. Now I know why. Yeah, so that should be a 20. So when we divide that by 2, that will give us a 10x. All right. So if I now do this little minus 10, look at what we currently have. Even though it looks different, Notice how I started with a 2x squared. Don't I still have a 2x squared if I were to distribute here? Still got a 2x squared. I start with a 20x. If I were to distribute this, 2 times 10 is still going to give me this 20x. And then I still have the negative 10 at the end. So this right now is the exact same thing that I started with. All right, just written differently. These are identical to each other. What I want you to now do, and this is what we did most of last week, if I gave you this, what would make this a perfect square? So fill in that number right there. Should be really easy because you have the squares over there, right, to look at. All right, don't we have 10 x's? And when I have 10 x's, doesn't the square get completed with a 25? So that's what we would add here. But now this 25, we're creating on our own. This wasn't part of the original problem. So we can't just add a random 25 in. So the way we were showing yesterday is we could, if I'm going to add here, I'm going to subtract it away from out here. But here's where you need to be careful. This isn't just a 25. Don't we have 2 of these 25s because we had 2 squares? And we can see that by distributing as well. It's really a 2 and a 25 make 50. We could then subtract 50 from the outside. When we now rewrite this, I have my x squared plus 10x plus 25. That will give us the negative 60 on the back end as well. We would then just recognize, hopefully, that if I have this, x squared plus 10x plus 5, then if I write it in vertex form, in a parentheses, don't we really have x plus 5 times x plus 5 squared, and then minus that 60? Okay. Okay, one more together, and then we're gonna have you try 3 and see if you can do 3. And then 4 is just a 3, but it looks the same. So for this one, I am gonna, again, for right now, we're gonna go ahead, sketch in the areas. So we have 2x squareds. So that means we have 2 of these little area models so that we have 2x squared corners. All right, without me prompting you, giving you hints, fill in what should go in these 4 corners here. All right, anybody confident what goes in each of those 4 blue boxes? Joe? Good. So these should each be a negative 4x. How'd you get that, Joe? Good. He took this negative 16. Since there are 4 boxes where we have to allocate those 16, if he took 16, split it evenly amongst 4. Okay, thank you. That's going to give us a negative 4 overall. Perfect. So now, if we know that, fill in this spot, and this bottom right-hand corner. So now we should be able to fill in the rest of those 2 areas. So fill those 2 guys in. All right, what now goes up? Well, let's do the bottom right-hand corner. What does this bottom right-hand corner now have to be? Matt? Good, we gotta be 16. So the only way we get negative 4x and a 16 is if both of these guys, and make sure that they're squares, if both of these are negative 4. So x minus 4, x minus a 4. So we have this all set up. What we can now do is say that I have 2 area models where I have x minus 4 times x minus a 4. That's what we've created up here. From these two guys here, when I write this in, I now have 16, 32 constants. So if I currently have 32 constants and I need to bring it down to a negative 6, we would obviously need to subtract, and we would need to decrease these 32 by how many to get down to a negative 6? See who's good with their negatives and such. Anybody feeling clever? Joe, what do you got? Good. Negative 38. This is our vertex form if we use that area model. But what you would hopefully notice, this is a little trickier, right? Oops. Trying to figure out that negative 38 was a little trickier. We probably would have eventually have gotten to it. Joe got to it. But that's a little harder when we start changing signs and it's a big gap. So this is a nice way. I think it's the easiest way to kind of do it all. It's just not necessarily quick. Yeah, kid. So see the constants I have here and here? So isn't that 32 constants? So when I write this right here, I'm writing these two guys. That means I have 32 constants accounted for. But if we look at what we're trying to create, we're trying to create a negative 6. So if I now did 32 minus 38, doesn't that give us the negative 6 that we're supposed to have? Okay. The other way you can do it, and this is kind of what we're going to do next, and this is, I think, is a little bit easier. If this is 32, we said we could just take and subtract it always from that constant, do a negative 6 minus 32. So whatever those constants are, subtracted away from that number isn't a negative 6 minus 32, also going to give you a negative 38 very quickly. And it's a little easier thought process. Okay. That's what we're ultimately doing when we go to this one. So now over here, and then we'll have you try the next one and see if you can get all the way through it. So we're going to start this problem again. We know that we want the 2 out in front of a parentheses. All right, that's what we have right here if we want it in vertex form. So the way we do that is we want to get rid of this 2. That means we're going to divide each of those by that 2. So that gives us the x squared. The negative 16 is a negative 8x. All right, so that gives us this. Right now, these are identical. We haven't added anything. We haven't subtracted anything. If I distribute the 2x squared, I get the first term. If I distribute the 2 to the negative 8, I get that negative 16x, and I have a minus 6. So we haven't added anything extra. But now, if I ask you to fill in this spot right here to make that a perfect square, what I'm really just asking you to do is come over here, and how did we make these a perfect square? Wouldn't we have added 16 to both of those to make it a perfect square? So that would have been the number we would have had here. So now this 16 is not in the original problem. So now we have to adjust because of that. If I added 16 here, didn't I really add 2 of those? So that's 32. So I just created 32 out of a nowhere. So I'm going to subtract 32 from that negative 6 at the end. All right, so when Caden asked that question, that's what we're really doing, is subtracting that 32 at the end. So what that would now give us is 2x squared minus 8x plus 16. And then notice we get that negative 38 this way as well. All right, and then vertex form, we just want to write this as a perfect square. And then that was the x minus 4 times the x minus a 4. And then we get the same thing either way. All right. Any questions on that? Okay, let's see where we are at. However you think you would do one of these, try number 3. And then we'll see where we are at now. And then we'll do one more. Number 4 on the back page is just a 3 in front of everything. It's the same process. But let's see if we can get number 3. on there you're supposed to have to create this constant. So, well, that's one way to approach it, but I have to, and I need 10. How many more do we need to add to it? 4, 6, 8, right? And that's up here, we got 4, 8, 12, 16, right? Okay, so when you write this right here, when you write this right here, that is just this part of it. If you put a 2 in front of this, that means you actually have another one of these, which you do, that's true. But because of that, you don't just have one constant, you add another constant right here. So we actually have 2 total when you write this. So you have written here, it's correct. That actually gives us 2 constants, which means we only need to increase by how many? We only need 10. We have 2 already. Yeah, so instead of plus 9, you would have plus 8. You have 1 each of those squares. Yeah, and if you're good, if you think you're good with that one, or if I told you you were good with that one, see if you can do number 4. Just make sure if you did it well. Don't forget the square there. Square there. This one actually don't. So we have to be careful about how this. You should have 2x squared. So here's 1. Here's 2. You should have 4 x's. Here's 2, 4, 6, 8 x's. So you're splitting these up where we do 4 spots out. So if I do it that way, how many am I going to have in each? Yeah, so these are all just 1s. So that's not going to change some stuff. These are all 1s. And what you have now is x plus 1. 2 of them. You have 1 up here and 1 up there. So now, how many constants do you have?
Yes. So what do you have here? We have 2.
Alright, you get both of you check your math.
But you told me we have to add 8. So we only have 2.
This is good.
Square, we get 2, right?
Where this is coming from,
We want 10.
it's just the area of this rectangle. So if I ask you, it's x plus 1, x plus 1. Yeah, but that's going to change your x a little bit.
Yeah, so you could always do that. We have the 2, right?
Like,
So just minus 2.
well, plus
It's not up here. Oh, sorry. Yes,
and
minus
then
2 would give us positive 8. That's plus 8.
so this is
Whatever you get one of these 2 boxes,
still constant.
just subtract whatever it was that you
That's what you get. So then now, that this has 1, but you actually have 2 of them. So that's what we then want to subtract away. Back. What's that minus 2? This is 8. And now I'm asking right this is for a square. Isn't that x plus 1? And I have x plus 1 squared. So that's then 8, right? Okay. So first we're going to read, right? You get it, 4 to 8. Like all of this, but look at that. That you get plus 1 times x plus 1, that's your square. And then you change your constant and you get. So if you had this x squared and then you had 2x, and then 1x here, 1x there, so what constant you have? All right. So with 3, I'm going to do it without the areas here, just a little more time, and then we'll go to 4. What I would do is take these 2, understand that that gives you x squared plus a 2x, and then we still have the 10 there. This here, exact same thing, just different way of rewriting it. When I add whatever completes this square right here, we need to adjust out here accordingly. I just can't add a random number to a problem without changing the problem. So if I ask you to make this complete square, and a lot of us are drawing these, which is totally fine, it's great. What we do when we did that, to get 2 x's, you would have had 1x here, 1x there. So that means in the bottom right-hand corner, to make this a perfect square, you would have 1. The 2 just means you would have a second one of those. If you wanted to draw a second one out, you could do that. But what we have just done here is we've just added this 1 out of thin air to make a perfect square. We just created that. It wasn't part of this original problem. It's nowhere to be found in here. So to account for that, we need to adjust on the back end so that we really are adding a 0, and we can add 0 to anything. So what we now need to do is subtract away however many constants I added here. And where this gets a little sneaky is this isn't just a 1. Remember, if we had drawn these out, you have a 1 here and a 1 here. We can tell that by the 2 in front. 2 times 1 is a 2. So if I have 2 constants, that's really what I've created in this problem. So if I just subtract 2 away from it, that's going to give me 8. So what we then have is 2, x plus a 1 squared plus an 8. Saw a lot of those eventually. So that ends up then being our vertex. Okay. All right. And then number 4. So some of us, if we're doing this pretty good, have already gotten this one done, which is good. So if you got through this, if you get this one right, then you're in pretty good shape. We can kind of get to today's stuff with the negatives and see if we can adjust for that. The reason eventually the areas just become a lot of work because now you'd have to draw 3 of them in. And that's reasonable. It's not awful. But what if I put a 4 in front of this? Things get a little bit crazy having to do that all the time. So that's why long term, it's nice if we don't have to draw them. But I am going to draw it as a reference eventually. So now, if I want a 1 in front of this, which I always do, we want to get rid of that 3 by dividing that by 3. So we're going to take those first 2 terms, divide them by 3. Again, the 11 we just ignore. We're kind of waiting for him towards the end. All right, when I do that, that gives me a 1x squared plus a 10x, which is good. And then to account for the 3, we just put that 3 that was there out in front. And again, what I want to make sure we understand is if I now redistribute this, if I reintroduce the 3 to x squared and 10, wouldn't that give us these 2 terms right here? That's how we know we haven't changed the problem yet. And then we still have our plus 11 hanging out at the end. So right now, these guys are the same exact thing. We haven't changed the problem at all yet. However, when I now complete this square right here, I am going to be adding a number that's not part of this original problem, and that's a bit of an issue. And that's why we got to adjust on the end. So this is where if we're getting good, hopefully we don't necessarily have to draw it out. If I took 10x, doesn't half of them go here, and then half of them go right here? So that would mean these are both 5s, and that puts how many constants in this bottom right-hand corner? 25. So that means to make this a perfect square, you would now add 25. This 25 was nowhere in this original problem. We just created that to make a perfect square. We can't just do that, right? That would be illegal. So what we want to do is subtract it from the back end. If I add 10 and then subtract 10, I really haven't added anything because that's 0. But where you need to be careful is this isn't just a 25. We have 3 of these. We would have had another one if you draw it out with the 25 in this corner, and then you would have had your third one with a 25 in that corner. So that's really 25, 50, 75 total constants when we put that in there. So if I've randomly added 75, I better subtract 75 so that I really have a net change of 0, and we haven't changed the problem. We don't need the area model. if you understand this is really 3 times 25 that's being distributed. So that's how you can also get 75 to know that's what we're subtracting away at the end. So if you got this, I'm going to leave these. Some people are still looking here. The 3 out in front. If I now write this as a perfect square, what we would have had is a bunch of 5s, x plus 5s, x plus 5s all over the place. So I have 3 of these x plus 5 perfect squares. And then I would do 11 minus 75, which is a negative 64. If you got that, that's pretty good. Okay. Hopefully walking out here today with a pretty decent understanding of this. Okay. Okay. Any questions on those? All right. Then go to the notes I gave you yesterday. Actually, I got to pull them up now that I think about it. So go to those notes that I gave you yesterday. Let me pull it up. And now we're going to make your head spin a little bit more. Because we're going to put a negative out in front of all that stuff. If it opens. There you go. So go to the problems we were doing. We skipped a couple. And we're going to go back and do the one that we skipped. If it opens. Getting there. All right. So letter B. So we should have done A. We should have gotten C done, correct? So now go to letter B, and now we get this little negative in there. So hopefully we're at a point. We can try to draw this out with an area, but using the area model with the negatives become a little trickier. So that is why, again, I would like you to kind of eventually, as you're getting more comfortable, understand that if we want this to be a 1, I'm going to divide by whatever number is in front of this. In this case, it's a negative 3. So we're going to divide those first 2 terms by a negative 3. That now gives me g of x to equal the negative 3 we're going to pull out so that it's been distributed. We're going to distribute it. This now just gives us x squared. These would have canceled. And then now a 6 divided by a negative 3 is a negative 2x. Just like every problem we've done so far, if I redistribute, so if I take this negative 3 and distribute, we're not going to actually do it. But do we agree negative 3 times x squared gives us this guy? And then the negative 3 times a negative 2 would give us this guy. And then we still got the negative 17 that's off doing his own thing. So we haven't changed the problem at all. We just wrote it a little bit differently. So real quick, this is what we've been spending a ton of time on. Complete this square. What would go in right here if I have an x squared and then I have negative 2x's split between those 2 corners? What number then is in the bottom right-hand corner for this area model? Okay, what do we think? So if I have x squared in the upper left-hand corner and I have a negative 2x split both ways in the upper right and bottom left, Matt, what number's in our bottom right-hand corner? A 1. Because we're basically just cutting this in half, squaring that, multiplying it by itself to get a 1. Now we've changed this problem. Now we've created this 1 out of nowhere. So on the back end, I need to subtract away whatever I just put on the inside. This isn't just a 1 though, right? Wouldn't we have distributed this negative 3 to that positive 1? So what I have really created is a negative 3. That's what I've added to this problem. So on the back end, I need to subtract that negative 3 from the number in the back. so that when we now go to rewrite this, we would have the -3 out in front. Hopefully we're understanding how to write this as a perfect square. If this is a -2x, we have 1 and 1 in each corner. That means this would be x and then a -1 squared. Now we're subtracting that -3, so we're really going to be adding 3, and then that should give us a -14. All right. That's our vertex form. I can now ask you what the vertex is, and you can tell me it's 1, -14. All right. All right. Any question on that before we go to this next one? Good. All right. Then go to letter D. This time, the number in front is a -1. We don't want it to be a -1. We want it to be a +1. So if it's not a 1, it's not a +1, we are still going to divide by whatever that number is so that we create a +1 in front. So the -1 is going to be outside of our parentheses. And then a -1 divided by -1 is just a 1x squared. The -8 divided by -1 is a +8, and then your x. And then we're going to make this a perfect square. We got to fill in this spot, and then we still got our little -10 hanging out in the back. All right, give you a minute, see if we could understand what we do in the next 2-3 steps. All right, what if we were to draw the little square out, and I have x squared and I have 8 x's total, what would be the number in the bottom right-hand corner? What completes that square? All right, Matt? That -2. So think about our area here. Joe, what do you think? Yeah, should be a 16. So think about this, Matt. I have the x squared here, right? Wouldn't this square and this square have to be 8x? So that puts 4x's here and 4x's here. So doesn't that mean I have a 4 and a 4 multiplied together to give us that 16? Okay. So 16 makes this a perfect square. The blue I just added out of nowhere. That's not part of this original problem. So we need to account for that in the back by subtracting it away. If I just create a 16 out of nowhere. So I'm going to subtract, but it's not just a 16 because we have this negative being distributed to it. So it's really a -16 that we added. So that's what we now need to subtract away is the -16 that we added on the inside. So this really becomes +16. So we'll have the -1 in front. Let me do this down here. Then this here, I actually drew it, right? Then we have x plus 4 times x plus 4 squared. And then the -10 and the 16 give us a +6. Okay. All right. This, you are going to get some homework on. Now I want to see if we can do this. So let me give you this. All right, you're just going to do, maybe we'll just just limit it to the first page right now. Yeah, I'll just have you do the first page. You won't worry about the graphing of all of these. So you're gonna do 1 through 10, and it's the same thing you've now been doing for the last 3 days. Can you take standard form, convert that into vertex form so that we can identify what our vertex is? All right. And I'll be curious how those go. If you have questions before you hand in tomorrow, we can certainly do some of them before you hand it in. All right. All right. So just 1 through 10. Don't worry about the back page right now. Stop the recording. Oh, yeah, good call. A lot of dead time. 5 minutes in.